This is Professor Dare of Sites. This algorithms video is about algorithms, analysis, and example. This first program here is going to print the 12 days of Christmas in quadratic time. It's a Python program. There's a variable called line1 template. It says on the ordinal day of Christmas, my true love sent to me. Ordinal is going to be replaced with 1st, 2nd, 3rd, 4th through 12th. And the various gifts are here in a gifts list. So we have an ordinals list, a gifts list, and this template. The code, the input size n is set equal to the length of ordinals, 12 for this example. And we're going to not count all the primitives. What's significant to compare the various algorithms here will be just counting the printed output except for the blank lines. So we have a count non-blank prints that we'll be incrementing. And there's a for loop here, an outer for loop and an inner for loop. The outer for loop goes through the 12 days, n being the length of ordinals, and the inner for loop takes whatever day you're on and counts backwards down from there using the current index and then stepping backwards towards 0. The -1 here is the limit, which is 1 less than where it stops. And so a nested for loops to do what we need to do. The innermost loop does the countdown, and this outermost loop prints the template line, replacing the ordinal with the actual ordinal value. And then the innermost loop, there's a little bit of trickiness with a difference here where it says partridge in a pear tree. On the first day it has to say a partridge in a pear tree. On the other days it's at the end and it says and a partridge with a pear in a pear tree. So this if statement here is handling that case. But the main point here is we have nested loops, one going through all the input and the other one partially through it. And the counts, there's a count non-blank prints here was incremented in this inner loop, and at the end of the outer loop it's incremented once as well. So once for the ordinal line that tells what day of Christmas it is that's current, and then one time in each countdown line inside here. At the end, after it does those loops, it prints some summary information, the value of n, the value of n squared. N is of course 12 in this program, but we have to think about what would happen if we change this to have more than 12 days. Suppose we wanted to count down 100 days or whatever number. So we have to think in terms of what's going to happen as the number of days would increase. But we'll look at this after we run it. Run this now. Hit F5. And we see the output here. We'll scroll up to get it from the beginning. On the first day of Christmas, my true love sent to me. That's the template line with the ordinal first being replaced. A partridge in a pear tree. And each day, 2nd, 3rd, 4th, 5th, etc., all the way down, we see the template line And then also for each day, the countdown. So on the second day, 2 and then 1. If we go up here to the 7th day, 7, 6, 5, 4, the countdown. If we look at the number of printed lines, not counting blanks, we see there's one template line for each of the 12 days, and then the other ones are a pattern of 1 and 2 and 3 and 4 all the way up to 12. We're adding the first 12 natural numbers and then 12 onto that. At the bottom of the output, down at the very bottom, which I'm going to have to extend the window here to see, we see the summary output. N is 12, n squared is 144. Here's a formula calculated. Counting the first 12 natural numbers, it's n times n plus 1 over 2, putting 12 in there. And then adding the 12 on top of that, we get 90. That's how many should be printed. In our count that's printed out is 90. And basically, this is a quadratic order. The coefficient of the quadratic is less than 1. That's why we have a smaller value than 144, but it still has quadratic behavior. If this was to have a larger input, it would grow very rapidly because of the quadratic behavior. And the reason it's quadratic is because of the nested loops, both going through at almost n items each. So that's our first example, quadratic time. Let's now go to a second example of the 12 days of Christmas. Here's our second version of the program. It's going to print the 12 days of Christmas in linear time. We have a list here called days, where each entry, each item in the list, is the text for that day. So there's 12 strings in the list, one for each day. The program takes length of days for the input size, which is 12. There's the print count, has a for loop just going through each day, prints the day for that index, a blank line, and adds 1 to the count. Its summary prints out n, the number of print statements that were counted, and a statement about that this is linear order. Notice that it takes up more memory. These strings here, there's a lot of repeated text that wasn't in the first version. So to get this reduced order of magnitude, this more efficient algorithm, time-wise, there was a space trade-off. Let's go ahead and run this. And move this window into view. Shorten it so we can see it. Here it prints out 12 days of Christmas. And down at the bottom we see that the count, the number of print statements, was 12. Linear time. Let's now go to a third example. In this example, this program is going to print the 12 days in constant time. We have an output string that contains the entire text output in one string. We set n equal 12 because that's the number of days, and we print the output. Set our print count to 1. It's only one print statement, does it all. Let's go ahead and run this. You can see it printed out everything, and at the bottom says n equals 12, and there's only one print statement. This has a constant time order of 1. the amount of memory that was used in this one was about the same as the linear one. We didn't really sacrifice memory. We got better time. We have one final example that will show exponential time. In this one, in order to get an exponential program, what was changed was to add something to the printout. What's going to happen is it's going to print some ribbons, ribbon lines after each day, but they'll double each day, the number of ribbons. So we have our days array here, days list, containing the 12 entries, one for each day, and a ribbon variable looks like this, ribbon, capitals, and there's a nested loop. The outer loop is going through the 12 days, and the inner loop is based off a number of ribbons, which starts out at 1, and it will have that many iterations based on whatever that number of ribbons is. So it starts at 1, and then notice that the number of ribbons is multiplied by 2 down here each day, so it's doubling. The number of ribbons is going to double each day, and they will be printed right after we print the day's text. This will result in exponential order of magnitude because of the doubling effect there. Even with only 12 as the input size, we'll see that this is very large growth in the output. And the comments down here in the summary says the count. We'll print that out, and it tells it will be exponential base 2. Let's go ahead and run this, and you'll notice it. Watch it run. It starts just, it's many hundreds, thousands of outputs are still streaming here as we're waiting for it to finish. And finally it finished. Down at the bottom it says that it printed 4,107 statements. If we try to scroll through it, there's thousands of ribbons. If we go to the top, you can see that the ribbons start out modest, 1, 2, 4, 8, 16, but the exponential growth rapidly consumes the time. We had to wait for this thing to finish. So we've seen quadratic time, linear time, constant time, and exponential time, all for the same algorithm. Some of them were simpler, some of them used more memory, but we can see here that, again, that exponential time is not practical. We don't want algorithms that do that. And there are ways, when you're willing to make trade-offs with time and space, to get more efficient runtime at the cost of memory. This concludes this video.